Okay, so we know that non-metals make covalent bonds. A covalent bond is two electrons shared between two atoms. Carbon is a non-metal. It's going to combine with hydrogen, oxygen, nitrogen, phosphorus, sulfur, chlorine, fluorine, and bromine, and that's pretty much it. So, let's do some more general chemistry. Rules for Lewis structures revolve around, because hydrogen's in group 1, only having one electron, therefore always makes one bond. Now, chlorine has 7 electrons. 6 of them are tied up in bonding pairs of electrons. Sorry, non-bonding pairs of electrons. Therefore, those red dots don't do any of the bonding. We should never really have called them non-bonding electrons, because guess what they do in organic chemistry? They do the bonding. So, if you have me for general chemistry, I really don't call the paired electrons non-bonding, because it just puts me up against an obstacle later on. The old way of calling these was a lone pair. So that was a lone pair of electrons here and a lone pair of electrons there. And those paired electrons don't bond the atoms together. That's the deal. They don't bond the atoms together to make a molecule, but they do bond the molecules together. So when molecules start to react, those are the electrons that we're going to use, not the unpaired bonding electrons that you talked about. So if you're in group 1 or group 7, and of course other things in group 7 would also have 7 electrons, 6 of which are not going to count towards your bonding motif. So your chlorines, your fluorines, and your bromines always make one bond. Okay, now if we go out from group 1, so I've got something in group 1 and I've got something in group 7. Obviously stuff in group 8 doesn't bond. They already have 8 valence electrons, therefore they have a closed shell configuration and they're not interested in reacting with other things. So if I move out from hydrogen into group 2, I've only got metals. And metals aren't going to do covalent bonding, which is the case when you get to 3 as well. There's boron in there. We're going to see boron one time. I'm going to skip over it. That then gives me carbon, which is going to make 4 bonds. And then out to nitrogen. Now we're going to start going back down again. We'll make 3. And then oxygen will make 2. And now all of a sudden I'm back in group 7. We'll always make 1. So we can count the other way. That if I am an oxygen, group 6, 1, 2, 3, 4, 5, 6, 6 electrons, 2 sets of those non-bonding pairs of electrons, and then 2 unpaired electrons that are capable of bonding. Oxygen is always going to make 2 bonds, always. Sulfur is in the same group as oxygen. They're both in group 6. So it's exactly the same thing. It has just the same chemistry, only it's much bigger and stinkier. It does the same stuff that oxygen does. with a couple of twists that make it difficult to work with. Okay, when I get to group 5, 1, 2, 3, 4, 5, nitrogen has 5 valence electrons, 2 of which are in a lone pair of electrons, non-bonding pair of electrons, and then I have 3 unpaired or bonding electrons. So nitrogen always makes 3 bonds. Phosphorus is in the same group. So it does the same thing. And then we've got carbon. And carbon has 4 electrons in its valency. And as we showed on Monday, that should be 1s2, 2s2, 2p2, which would only give it 2 unpaired valence electrons to bond with. But it does some trickeration and gives itself the sp3 hybrid, and now is capable of making 4 bonds because it just rearranges to have 4 unpaired electrons. Okay. And then you do what you did in general chemistry. This is your jigsaw puzzle. Remember the rules for living structures? You start with that. Then atoms combine in a way that every atom in your new molecule has 8 valence electrons. Asterisk, except for hydrogen, which is only capable of holding 2. So you want all of the atoms in your molecule to have a closed shell configuration. There's going to be 2 electrons for that one, and then 8 electrons for all of these. You bond the molecule, the atoms in the molecule together covalently, which is by sharing electrons. One from here and one from there. If an atom appears only once in a chemical formula, there's a good chance that that atom is at the center of the molecule. If an atom appears multiple times in a chemical formula, chances are that that atom is on the outside of the molecule. Hydrogen and chlorine and fluorine and bromine can only make 1 bond, therefore always have to be on the outside. Cannot be between 2 atoms, because it cannot bond to 2 things at the same time. It can only bond to 1. So hydrogen is always on the outside. It's always a terminal bond to a hydrogen or a chlorine or a fluorine or a bromine. Okay, let's look at our simplest molecules. Our simplest organic molecules are hydrocarbons. They contain only carbon and hydrogen. A subcategory of hydrocarbon is called alkane, and an alkane is what we call a saturated hydrocarbon. The words saturated and unsaturated has entered into the lexicons through nutrition, where we have saturated fat and unsaturated fat. It's the same meaning. Saturated means contains exclusively single bonds to hydrogen. our simplest alkane only contains one carbon. So what we would do, the way that we would teach that in general chemistry, is you write your bits and pieces down. You write a carbon, it's got 4 dots, and then you write 4 hydrogens, and you put them together, okay? So CH4, that kind of predicts to me that the carbon's going to be at the center. And the thing that appears multiple times in the chemical formula is probably going to be on the outside. That wasn't a strict rule. It was a probably. Only appears once, probably in the center. Appears multiple times, probably on the outside. Oh, my little tiny bit of chemistry knowledge tells me hydrogen can only make 1 bond, therefore it always has to be on the outside. So you put your carbon where it is, and you introduce it to Mr. Hydrogen. And I have 2 electrons shared between 2 atoms. I just made a covalent bond. And I have 2 electrons shared between 2 atoms. So that right there, that's covalent bond. And I have 4 of them. So when I look at what this hydrogen is experiencing, this hydrogen right here, that hydrogen is experiencing 2 electrons. One that it owns and is sharing with the carbon, and one that the carbon owns and is sharing with the hydrogen. Covalent bonds are shared electrons. So that hydrogen now has a covalency of 2. In the first period, we only have space for 2 electrons. Therefore, it's got the closed shell configuration. It's locked out. It's not going to do any more. And then when we look at the environment that the carbon is in, oh, that carbon has 8 electrons. And the atoms inside a molecule will continue to react until they reach the octet rule, until they reach 8, at which point they stop. So, got my octet rule, is satisfied. This is a stable molecule. This, as written, I'll write it out again, dot, 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 dot. That is a Lewis structure. Lewis structures show you the electron dots. If during the course of this term you were ever asked to show the Lewis structure, and you show me a representation with the line, where the line represents a bond and the bond represents 2 electrons, you have not drawn me a Lewis structure. You've drawn me something else. This is a Kekule structure. There will be times when we need you to show us that you recognize the fundamentals of how to construct molecules, and you know what you're doing with the electrons. So sometimes we will specifically ask for a Lewis structure. Lewis structures show the electrons. Kekule structures have dashes to represent the covalent bonds, and of course, covalent bond is 2 electrons shared between 2 atoms. Kekule structures, also known as, sometimes it goes by structural formula. Did you write it out? That's as simple as it gets. And that molecule, CH4, anybody know what that's called? complexity, we get to C2H6, which is our next simplest hydrocarbon. I'm going to erase that. Make sure, if you want to make a note to yourself about Lewis structures and Heck-Hewitt structures, write that in, because it's going away. Okay, I'm going to have 2 carbons and 6 hydrogens. Now the deal being, here, the first thing that we wrote down, hydrogen can only make 1 bond. So there's no way that you can describe this that has hydrogens at any place other than on the outside. Those 2 carbons have to be bonded to each other. There is no way that you can represent that molecule without the carbons being bonded to each other. I've got 6 hydrogens, and if you fill the first carbon with hydrogen, then there's nowhere for the second hydrogen to go, because the hydrogens can only make 1 bond at a time. And if you bond them to this hydrogen, to this carbon, then that carbon can't go anywhere else. That tells me those 2 carbons are stuck together. We have colored pens. So here is carbon number 1. Here is carbon number 2. If I make a covalent bond, there it is, 2 electrons shared between 2 atoms. I make a single covalent bond between those 2 carbons. Then what I do is just mop up all the other available spaces. Every other available unpaired electron, bonding electron, gets a hydrogen. And now each one of these hydrogens has a closed shell of 2 electrons, and this carbon, the black one, has 1, 2, 3, 4, 5, 6, 7, 8. And the blue one has 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied for everything. Okay. This one is called, that's ethane. It should not be a leap of imagination to figure out what comes next. So we have a naming system. That goes meth, F, prop, bute, pent, hex, hept, oct, known, and dec. Those are the prefixes that we will use to describe our molecule. Now, all of this family that only contains hydrogens and carbons in combination and only contains single bonds, they all end in ane. So methane, CH4. Ethane is C2H6. Use your enormous human brains and predict to me what the chemical formula of propane is.
C2H8.
C3, H8. You haven't figured it out just yet. You will in a minute. What would butane be?
C4H10.
And pentane?
C5H12.
And hexane?
C6H14.
C7H16.
16.
And C8H.
18.
And C9H.
1.
And I've kind of gone, I have to write them in a different font size. CH4, C2H6, C3H8, C4H10, C5H12, C6H14, C7H16, C8H18, C10H. It's not immediately apparent to you yet. This is following a trend. It's following this generic formula. Because carbons have to have 4 bonds. If there's nothing other than hydrogens to attach to, you put 4 hydrogens on there. But as soon as you start bonding them to carbons, one of those bonds goes away. So you get 2 for every carbon, 2 for that carbon, and 2 for that carbon, however long the chain is, and then 1 for each end. So whatever my number of carbons is, I'm going to require 2 times that amount of hydrogens, plus a couple to stick on, 1 at the front and 1 on the back. Okay? So let's do the easy one. Right? I've got 3 carbons. They each have 4 electrons. They have to be bonded to each other, and then I put a hydrogen here, and a hydrogen here, 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 here, and a hydrogen there. So you get each of these little building blocks. Each of these is a CH2. We call that a methylene. Little CH2. That's our CH2 building blocks, however long the chain is, and then plus this fella, and then that fella. Okay? Count the number of carbons you've got. Double that number to get the number of hydrogens, and then add 2. We're not normally going to ask you to do this in the forward direction. Figure out what the formula of this thing's supposed to be. Normally, we'll give you the formula and then ask you, hey, show me what that shape is. So let's do that. Let's do it backwards. So the prefix, meth, eth, pro, but, blah, 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 tells me the number of carbons, and then ane tells me, nope, wrong part. The ane tells me contains only carbon, 2 hydrogen, single bonds. Now, they're always going to be single bonds. Contains only C to H, C to C, single bonds. Okay. Now, after a while, it's going to get tedious drawing all those dots in. And honestly, after some of your handwriting is shocking. I haven't met you yet, but I can tell that some of your handwriting is going to be shocking. And when we ask on a test question, we learn not to do this. Draw me the Lewis structure of this molecule. And we got a couple of random things in there. You know, I don't know. That's like my astrological star sign right there, and that could be a nitrogen. I'm not sure what that is. So you get 0 points. And then you come and you argue, yeah, but look, no, that's my carbon, and here are all my dots, and no, I can't read that. So it does get tedious, and we don't need the Lewis structures. So your calculate structure just represents the bonds. The carbons have to be bonded to each other. That's going to leave 6 spaces here and 1 on each end to bond to something. If they're hydrogens, they can only bond one way. Okay? So when we ask for the structure, give me the calculate structure, give me the structure of formula. Okay, so let's do it. Go draw C5H12. Going to give you 75 seconds to draw that molecule. Okay, so I may have said, almost certainly said, on the first day that organic chemistry is not difficult. There's no math. You follow very, very simple rules. Lewis structures have incredibly straightforward rules. The only difficulty is the amount of contents as it relates to permutations for that question. So, on my way out of the room, I said, draw C5H12. I did not say draw pentane. One, two, three, four, 5 carbons in a row. Each of those carbons has the capability of making 4 bonds, because it's an sp3 tetrahedral. We'll show you the geometry of it later. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is my 10 hydrogens. That is pentane. And if I had asked you to draw me the structure of pentane, and you wrote that down, you'd get 100% of the grade on that question. Did anybody write anything other than that? Because it's not what I asked for. I didn't ask for pentane. I asked for C5H12. Bear with me. 1, 2, 3, 4 carbons, 5 carbons, stuck together, only not in a straight line anymore. Now it branches. How many hydrogens do you think that leaves possibly exposed to bonding? 1, 2, 3, 4, 5, So you're down to 50% of your score, because you only wrote one possible answer. Because I didn't ask for pentane. If I'd have said pentane, that's pentane. This is not pentane. This is something else. But it is still C5H12. In naming a molecule, you name the longest chain, and then you end in ane. What's the longest chain in my second molecule?
4.
So this is a 1, 2, 3, it's 4 carbons long. So this is a butane. It's some kind of modified butane, some mutation. But the longest number of carbons, the longest chain in this molecule is 4 carbons long. Okay, so now what we're going to do is the longest chain. Oh, by the way, is there anything in this molecule that is not a single bonded carbon or hydrogen? No. So this is still a hydrocarbon. It is still an alkane. Its name still ends in ane. We find the longest chain, and then we tag onto it an adjective. And in chemistry, our adjectives are going to end in ill. We're going to name the length of what we're going to call the side group, also known as a substituent. And I have red and blue and black. So if these 4 carbons are my long chain, then this is now something dangling off that long chain. That's now my substituent. How many carbons are in that substituent? 1. So it is a methyl. So this gets to be methyl butane. And that's almost the correct answer, except the thing that goes right here. I had the red pen in my hand. Is the numbered position that the substituent occupies. So this is a straight line. All of those atoms are bonded together in a chain. This one is branched. What I'm asking for here is at what numbered atom did that chain branch? And we put the number, and then we put a hyphen, and all of this, because it's covalent, that is all one word. It might look like there's a gap between the methyl and the butane, but there isn't. Covalent molecules are all one word. Ionic compounds have a space in them between where the positive cation is and the negative anion is. Sodium space chloride, metal space non-metal, cation space anion. Covalent molecules, all one thing. So this is one word. So that's 3-methylbutane. I counted the chain, in the Western world, we get into the habit of reading molecules from left to right. Why? Nobody said that was a rule. Just because we read text from left to right doesn't mean that we should read molecules that way. You read them any way that you want to. But you should number to the lowest numbered position. So is that really 3-methylbutane? Not if you read it from right to left, it's not. It's now 2-methylbutane. Turns out 2-methylbutane and 3-methylbutane are the same thing. That's going to happen. But we condense our words down to the best possible explanation. Okay, so the reason that we do that is if you want to go buy that molecule, it's going to be on the chemical company's website or in their catalog using the best possible name. So you're only going to find 2-methylbutane in the catalog. You go, but I need 3-methylbutane. I've been asked to do this experiment and I need to find this molecule, and I've checked and its name's 3-methylbutane. And you call up the manufacturer and no, because you talk to a salesperson, not a chemist. Oh, no, we've got none of that. We've only got the 2-methylbutane. Okay. Same thing, but you use the best name that you can. Now, the reverse of that. If I said to you, draw me 3-methylbutane, you could all do that, right? That would be the wrong name, but you could all draw it, and it would be this. So if your name, even though it's wrong, even though it's not the best, it's not wrong, it's not the best, even if your name is not the best, but it adequately describes your molecule, you are not going to get hammered from me for that, okay? But there's a better way, and you should try to find the better way every time. Okay, so if I said draw me C5H12 and you only drew me that one, then it looks like you're only getting 50% of the points. Unless, of course, there was another variation. Is there another variation?
You want us to journal with the dots?
No, no. Just one bonds, one calculate structure.
I have a question.
Yeah.
How did you know to branch it at that one?
What if I did this? Want to still be on camera? What if I did, I know that if I write them all out in a row, that I've already described it. So here's what I'm going to do. I'm going to snap that molecule, that atom off the end, and I'm going to put it there. What's my longest chain? I just made pentane again. Because nobody says that you have to read from left to right. What if I do it that way? You don't have to write from left to right. I can write top to bottom, and I can write going around corners. It's still 5 carbons in a chain. Each of them, it's called catenation, where carbon loves to do this, where they attach to each other. It goes 1, 2, 3, 4, 5. They're in a chain. Now if I take off one end and put it on the other, I've achieved nothing. 1, 2, 3, 4, 5. They're still where they are. So what I have to do to make something new is take an atom off the end and then put it in the interior part, so not on what's left now as a new terminus. So I could put it here, and that would make me,
So that's why the 2 and the 3 are the same.
that would make me 1, 2, 3, 4, 2-methylbutane. Or I could put it here, and that would make me 2-methylbutane. Or I could put it here, and that would make me 2-methylbutane, which just leaves me here, and that's called 2-methylbutane. So it looks like I've found all the possible answers then. No. When you think you've exhausted all your possibilities, take another one off. Okay? Take another one off. Now watch what happens. I put it here because I'm a dummy. What have I made? I'm going to use a different color. Okay? I'm an idiot and I've lost track of what I did. What have I made?
2-methylbutane.
It's still 2-methylbutane because I haven't listened to my own advice. I can't put it on terminal carbons. Oh, what about now? What is it now? Yeah, it's still 2-methylbutane. 1, 2, 3, 4 carbons in a long chain. And if I count from this end, 1, 2, 3, 4, it's still 2-methylbutane. What's that called? What's my longest chain? Okay, do we want to be conventional and read this from left to right? Let's not get into the habit of doing that. Because from left to right, it's 1, 2, 3. That's my longest chain. If I go around a corner, 1, 2, 3, it's still 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? My longest chain is 3 carbons long. Therefore, this is a propane of some description, and it has substituents, plural. It's got 2 of them. We'll make that carbon number 1, that carbon number 2, and then carbon number 3, and then carbon number 2. There is a methyl on the left, and a carbon number 2. There is another methyl on the right. Mono, di, tri, tetra, penta, hexa are now going to be the numbers 1, 2, 3, 4, 5, 6 that describe multiples of. So this gets to be, it's a prop, that's my longest chain. It's an ane, I can only see single bonds. And there's a methyl, meth for 1 carbon. Here's my substituent, 1 carbon. So that's a methyl. And I have 2 of them. There's 1 on the left and 1 on the right. So that is dimethylpropane. You need to tell me where the substituent branches from my chain at the lowest possible numbered position. And that position was 2. So I write 2 with the hyphen. And at this point, I've almost got the name right, but I'm not right. Because there are 2 substituents. You have to tell me where they both are. It's redundant, but you tell me anyway. Both of those methyls are at the 2. 2, comma, 2, hyphen, dimethylpropane. all one word. Okay, so for multiple substituents, we don't need to go up higher than that. You're never going to have. It's very unlikely that you have more than 6 of the same substituent. It's really unlikely.
You wrote them wrong. Mono and di, they're kind of in the same place.
Well, I'm going to solve that problem for you, because our words, our names, are going to start to kind of get long. And if we start to include mono in everything that we do to describe just one occurrence of our substituents, our names are going to get unnecessarily long. So the mono exists, but we only use it if there's something really unusual. And the unusual kind of happens when a molecule normally has more than one of something, and in this particular case, it only has one. And we'll name that one specially. So the monos never come up. Di, tri, tetra, penta, hexa will be good enough. All right, we've got 5 minutes. Let's branch out. Haloalkanes contain carbon, hydrogen, chlorine, it's usually chlorine, or bromine, or fluorine, and only single bonds. Draw and name C3H7Cl. Now, the simple, really tiny hydrocarbon backbone is still fundamentally simple at prop. I cannot take that off. If I take that carbon off and try to put it somewhere else, I end up putting it back on a terminal, right? So I don't have to worry about the carbons being in isomeric positions. Those last two that we drew were called isomers. Same formula, different arrangement of atoms. Okay, so this is my backbone. I've got 1, 2, 3, 4, 5, 6, 7 hydrogens, which means if I'm not bonding those carbons to hydrogens, the place left over has to go to the chlorine. So the name for this would be, that is 1 chloropropane, all one word. Is it the only isomeric structure for C3H7Cl? What if I took that chlorine put it here. How about now? What have I made?
1-chloropropane.
Yeah. 3-chloropropane is the same thing as 1-chloropropane. Just you reading it that way and reading it that way. And look, oh, it was pointing up on this side, but now it's pointing laterally out. Doesn't matter. Doesn't matter. It's all about attachments. That is still 1-chloropropane. So what's my other option?
-2.
Put it at the 2. This is 2-chloropropane. And 1-chloropropane and 2-chloropropane have the same chemical formula, but they have different chemical behaviors. We're going to use one of them for one purpose and the other one for something different. So when you call up the manufacturer and say, I need 50 liters of chloropropane, they're going to say to you, which one? What? Which type of chloropropane do you want? Do you want the 1-chloropropane or do you want the 2-chloropropane? Because there are going to be reactions that this one can do, that that one cannot do, based on structure. These are called isomers. They are structural or constitutional isomers. They have the same formula, but different arrangements. Okay, I think you should read ahead a little bit. Either read the book or read the lecture notes that are posted on Blackboard. Because it's the same thing for the first couple of days. We're going to do just example after example after example. We're going to get through naming, because if you can, you need to get through naming. You need to, when I say a word, we all need to be able to imagine that word in our head and be able to write it down on a piece of paper. When you converse between yourselves and with me, we need to get through that language barrier. So go look at the lecture notes and